Post-depositional modification of sedimentary layers. When a sediment is generally deposited as layers, it may contain some features such as cross-bedding, wave ripples, or horizontal lamination, which refer to a primary sedimentary structure. This sedimentary structure may be subject to modification by fluid movement and gravitational effect if the sediment remains soft. Soft sediment deformation is generally termed for changes to the fabric and layering of beds of recently deposited sediment, and these deformation structures are mostly formed as a result of sediment instabilities caused by density contrast and by movement of pore fluid through the sediment. When the sediment is deposited, it will be saturated with water, and container deposits will also be saturated by groundwater. And some burial by more sediment usually will be leads to greater expansion of the pore water, except for the trapped water within the impermeable bed above. Because of the trapped water, it becomes more overpressure, and when it cracks, its overlying layers allow fluids to be released. It travels at high velocity upward. And then the fluidization will happen when the rapidly moving pore water, and it will be carried upward with the moving water, and venous sediment can be carried easily upward, so the process of filtration will be occurs, and fine sand is carried away by the fluid. It will leave behind the coarser and more corrosive material. Meanwhile, the liquefaction is a shorter-term process that will be happens when a mass of saturated sediment is affected by a shock, which is like earthquake, and it's become momentarily liquid, behaving like viscous fluid. And the soft sediment deformation will be grouped into structures due to sediment instabilities, liquefaction, fluidization, and loading, although these are not mutually exclusive categories. Next is the structures due to sediment instabilities. First is the slump and slump scars, which is formed from the result of gravitational instabilities in the sediment pipes. And when a mass of sediment is deposited on a slope, it is often unstable, even if the slope is only a matter of degree or so. And if some subject to a shock from an earthquake or sudden addition of more sediment failure, it may occur on surface within the sediment body, and it may lead to slumping of material. Next, we got the slump beds, which deform into layers and show a fold structure with anticlines oriented in the downslope direction. Now we have the slump scars that was removed from slump material on the surface left, and it can be recognized in the stratigraphic record as spoon-shaped surface in the 3 dimension, and they range from a few meters to hundreds of meters across, and commonly in delta sequence, but also can occur in material deposits on the slope. Next is the growth fault, and growth fault are considered to be thin sedimentary structures that is they form during the deposition of a package of strata, and they're mostly commonly found in a delta front succession. And the spoon-shaped faults are formed when the failure occurs on the weak horizon and it propagates to upward, and it also known as the listed faults. Because there have been a movement on the beds above the faults over the curved faults, and it will result as a characteristic rotation of the beds. And growth fault can be distinguished from post-depositional faulting because a single fault affects only a part of succession, while the overlying beds are unaffected by the fault. Is the structure due to liquefaction. First is the convolute bedding and convolute lamination. Convolute bedding and convolute lamination is a result of the local liquefaction of deposits, and the structures range from slight overstepping of cross strata to the development of high folder and confronted layer. And the deposition is on a slight slope or rather a shear stairs on the material due to flow of line fluids, and the flow is later tend to be asymmetric, anticlines pointing downslope or in the direction of the flow. Convolute lamination is particularly common in the turbidites, and it can be seen within the laminates and cross-laminate parts of the bed. Next is the overturned cross stratification. Sand deposits may be avalanching down to the lee slope of subacastune and loosely packed and saturated with water, and they are easily liquefied, can be deformed, shear stress, cause strong rents over of cross beds, and the sharing of the upper parts of the cross bed will be creates a characteristic from recumbent cross bedding or overturned cross stratification. Next, we go to structure due to fluidization. First is dish and pillar structures. Dewatering structures are formed by expulsion of pore water from a bed, and this structure is a concave disruption which a few centimeters to 10 centimeter upward movement of fluids. And the pillar structure illustration, which is called illustration pipes, is vertical water escape channels or simple tube or the vertical sheet-like form, and it's often occur together but also can form separately. Next is the sand volcanoes and extruded sheets. Sand volcanoes is a liquid sediment that's brought to the surface in isolated pipes emerge to form a small sand volcanoes. And this eruption of sand on the surface can be preserved only if a low energy condition prevent the sand being rewalked by current. The sand brought to the surface usually as an extruded sheet of sandy sediment, and this sheet can be difficult to recognize if the connection with an underlying that cannot be established. Is a forming series of sand can form but can also be difficult to identify. Next is the structure relates to loading. Load case first is a low density sediment happens overlying high density sediment, and it's became an unstable situation. The load case formed where the higher density sand has partially sunk into the underlying mud to form downward facing bulbous structures, and the mud may also become forced up into overlying sandbed in forming the flame structures. The load balls of sand may become completely isolated within the muddy beds, and these called as ball and pillow structures. It's common as base of sandy turbidite beds and other situations where sand is deposited directly on wet mud. Next is the diaphorism. In case where the instability due to density difference between layers or of consolidate sediment, it results in movement of material on the larger scale, and that's known as diaphorism. And this process can occur in a range of rock and sediments, and commonly observed where the density contrast is large and the low density material is relatively mobile. And the bulk density is determined by two factors. First is the density of minerals, and second is the proportion of the material that is occupied by pore space filled with the gas or liquid. There's two types of diaphorism that is commonly, which is the salt diaphorism and mud diaphorism. And two important implications for sedimentology and stratigraphy is first is diaphoric structures can create local heights on the sea floor that may become the locus for carbonate development. And second is diaphorism can create subsurface structures that can be traps of the hydrocarbons. As we go to salt tectonic, is a diaphoric movement of salt deforms the overlying structure. The pressure that required to cause halite to behave plastically can be generated by only a few hundred meter thickness of overlying structure, which is its overburden. And because of the lower density, the halite may move up in areas where the overburden is thinner or weakened by fault, and it's by create of salt dome. Last is the mud diapers. It's an intrusive structure characterized by slowly upwards migrating mass of clay-rich sediment and fluid discharge, and it's common feature of in the muddy delta succession.
Diagenetic processes, and these are the subtopics we are going to focus at. Diagenesis versus metamorphism. Characteristics alteration of sediment after deposition due to physical and chemical changes are called diagenesis. They occur at low temperatures, typically below about 250 degrees Celsius and at a depth of up to 5,000 meters. Metamorphism involves the destruction of original sedimentary fabric and occurs at higher temperatures, typically above 250 degrees Celsius to 300 degrees Celsius at a higher pressure in a deeper condition. Now let's have a look at compaction under burial diagenesis. The accumulation of sediment causes older deposits to be covered by younger material that exerts an overburden pressure that acts vertically on a body of sediment and increases the mass on top. Loose aggregates changes the packing of the particles under moderate pressure, resulting in increased density of the sediment. Pour water in the gaps between the grains is ejected in this process, and particle repacking lowers the volume of the sand body by 10%. Weaker grains in sandstone may be distorted by the pressure of stronger grains. For an example, fracturing in quartz. Mud deposition contain up to 80% of water by volume. However, this drops to roughly 30% after 1,000 meters of burial. Here are some examples of pre-compaction and post-compaction, uncompacted and compacted, and there's a fun fact as well. Certain sediments such as bound stones formed as coral reefs may not be compacted at all under the initial burial. In addition to reducing the thickness, compaction has little effect on the horizontal layer of the deposit. The internal sedimentary structures such as cross-stratification can be slightly changed, and the angle between the crossed strata and the horizontal plane can be slightly reduced. Differential compaction. When a lateral shift in sediment type occurs, differential compaction develops, in which one part of a sediment pile compacts more than the adjacent part. Example, lime muds deposited around an isolated patch reef, a sandbar surrounded by mud, and a submarine channel cut into muds and filled with sands. The finer material will compact to a greater degree than the sand body or reef under overburden pressure. Under compaction, the finer sediments will drape around the isolated body. In river successions with sand-filled channel bodies surrounded by overbank mudstones, the differential compaction effect is less prominent. As a result, overburden pressure on overbank muds and channel sands might just have the similar effects. Ripple and dune bed forms can cause mud layers to drape around the sand lenses. Where there is early cementation, local compaction effects also occur around nodules and concretions. Here's a picture showing an example of differential compaction. Next, pressure solution and dissolution. The burial of sediment under layers of strata results in overburden pressures that cause more extreme physical and chemical changes. In sandstones and conglomerates, the pressure is concentrated at the contacts between grains or larger clasts. In the presence of pore waters, diffusion takes place, moving some of the mineral material away from the contact and reprecipitating it on the free surfaces of the mineral grains. Results in grains becoming interlocked, providing a rigidity to the sediment that it becomes litified. Beds of limestone may show extensive effects of pressure dissolution. Next, compaction effects. Clasts will be in contact primarily at the place where they touch or point contacts if the sediment has been subjected to a very little overburden pressure. Changes in packing reduce porosity, bringing the edges of more grains together as long contacts. Pressure solution between grains results in concavo-convex contracts where one grain has dissolved at the point of contact with another. Under very high overburden pressures, the boundaries between grains become complex, such as contacts. Here are some examples of compaction effects. Chemical processes of diagenesis, cementation. Eugenetic. Cements are generated at the sediment water and sediment air interfaces. They are syn sedimentary or formed very shortly after deposition. Mesogenetic. The majority of chemical changes occur in buried sediment that is saturated with pore fluids, and these cements are generated at this stage. Telogenetic. Development of cement during uplift. Chemical interactions occur between the grains, the water, and the ions dissolved in the pore fluids during these diagenetic stages. These reactions occur at low temperatures and are often very slow. They require the dissolving of some mineral grains, the formation of new minerals, the recrystallization of minerals, and the substitution of one mineral for another. Next, we have nodules and concretions. Irregular cemented patches are normally referred to as nodules, and most symmetrical, round, or discoid features are called the concretions. Subterranean concretions. The interior of some carbonate concretions in mudstones display an array of cracks that are often filled with sparry calcite. They form during the early stages of burial of the sediment. Flints and other secondary cherts. Chert can form directly from siliceous ooze deposited on the seafloor. They may also form in concretions or nodules as a result of the concentration of silica during diagenesis. And finally, we have color changes during diagenesis. Reducing pore waters may change the color of the sediment from red to green. Diagenetic color changes are obvious where the boundaries between the areas of different color are not related to primary bedding structures. In fine-grained sediments, reduction spot may form around particles of organic matter. The breakdown of the organic matter draws oxygen ions from the surrounding material and results in a localized reduction of oxides from a red or purple color to grey or green.
Assalamualaikum, my name is Najwa and I will present about clastic diagenesis. The word clastic is referred to the metal of fragments of pre-existing rock, and the word diagenesis is the process that describes physical and chemical changes in sediment caused by water-rock interaction, microbioactivity, and compaction after their deposition. The early stage of diagenesis in terraneous clastic rock is mainly characterized by burial compaction as overburden pressure expel water between grains and reduce the porosity. The mesogenetic cements are much more extensive than early stage cement in most clastic rock, and it's mainly involves the growth of autogenic minerals such as quartz, calcite, and clays. Calcite is an important cement in many sandstone and conglomerates that deposited in marine environment, while quartz cement in sandstone occurs as ataxial overgrowth, and they form adjacent to pressure solution contacts by diffusion along grain boundaries. The silica cement can be found when there is an absence of calcium carbonate, for example in quartz-rich sand that deposited in a continental environment. The clastic diagenesis is divided into three parts, which are diagenesis and sandstone petrography, clay mineral diagenesis, and diagenesis of organic matter in marine mud. Next is the diagenesis and sandstone petrography are divided into three cement, which are silica, carbonate, and clay mineral cement. The silica cement is a refractory mortar suitable for laying silica brick, which is an excellent admixture for concrete as it leads to better engineering properties. It can also reduce thermal cracking that caused by the heat of cement hydration, improve durability to attack by sulfate and acidic waters, and also increase strength. The silica cement in quartz sandstone is usually seen as overgrowth of silica on the surface of some of the quartz grain. For example, as the silica precipitate out of the pore fluids, it nucleates on the surface of quartz grain and result in growth of the quartz crystal. The new growth of the crystal will be an extension to the crystal structure, so the orientation of the crystal lattice in the overgrowth will be the same as the host quartz grain. The overgrowth will show a clear crystal face when there is a space between grain. We can recognize a quartz overgrowth in this section by switching between plane polarized light. Next is carbonate cement. Carbonate cement is widely distributed in various sedimentary rocks and appears to be one of the commonest cement types. High content in clastic rock is seems possible to regard them as rock-forming components equally with common quartz, feldspar, fragment of rocks, and so on. There are two types of carbonate cement, which are beach rock and hard ground. Beach rock is type of carbonate beach sand that has been cemented together by a process called sedimentary cementation and contain meniscus cement or penda cement, while hard ground are hard crust of carbonate material that form on the bottom of the ocean floor and below the lowest tide level. If a porous sandstone is cemented by calcite, all the spaces between the grains may be filled by a mosaic of interlocking crystal of sparry calcite, and the size of the crystal may vary from very small crystal between the grain to large poikilotopic crystal. Lastly, clay mineral cement is the most important minerals that destroy permeability in sandstone and excellent as clarify and absorption material. It is used in many industrial applications such as paper, paint, petroleum, and so on due to their versatility, abundance, and low cost. Direct precipitation of clay mineral belonging to the illite and smectite groups can occur from pore waters and form a cement in sandstone beds. Illite that form has a distinctive filamentous structure that can be recognized in scanning electron microscope image of the rock and making it possible to distinguish this cement from the trickle clay mineral. Next, clay mineral diagenesis are characterized by the addition and incorporation into them of Me ions such as magnesium, sodium, aluminium, potassium, and so on. It's composed mainly of silica, alumina or magnesia or both, and water, and commonly formed by the prolonged chemical weathering of silica-bearing rocks. It is also can form locally from hydrothermal activity. The mud that deposited on the seafloor contains 80% of water and cause a compaction and considerable reduction in muddy sediment. During burial and increasing temperature, the clay minerals undergo a range of change in mineralogy that determined by the original composition of the material and the temperature. When the burial and the degree of crystallization increase, it's possible to use illite crystallinity as measure burial temperature, but when the illite is stable, it can easily rework into a sediments. Last but not least, is diagenesis of organic matter in marine muds. The shallow marine environment are regions of high biogenic productivity, and the mud deposited on the seafloor of the shelf is rich in the remains of organism. According to Burley et al. 1985, the diagenesis of organic material take place in a series of depth-defined zones. Organic material is defined as a subject to a bacterial oxidation, which is a process that dominates the upper few centimeters of the sediment, where it is oxidated by diffusion and bioturbation. Bacteria are involved in sulfate reduction to reducing sulfate ions to sulfide ion and ferric ion to ferrous ion. When the sulfide is precipitated, the ferrous ion react with sulfide ion to form pyrite, which is iron sulfide, and at the deeper level, the sulfate ion not remain.
Hi, I'm Hafiz. I'm going to explain to you about carbonate diagenesis. Cement in carbonate rock are mainly made up of calcium carbonate derived from the host sediment. Deitrification of aggregate and carbonate material can occur simultaneously with deposition in any setting, where there is either a lot of seawater being circulated through the sediment or where sedimentation rates are low. In one tropical shallow marine environment, the seawater is often saturated with calcium carbonate and sedimentation can take place on the seafloor, forming hard ground, especially when sedimentation rates are low. Although water is undersaturated with calcium carbonate and solution of carbonate material can occur in non-marine environment, calcite sedimentation occurs in both the puddle zone and phreatic zone. The precipitation of the calcite to form the cement is due to the degassing of water, which the result deposit of stalactite and stalagmite in cave. In soil, calcite precipitation forms cement as resolute and calcrete as a result of the evaporation of groundwater and the addition of calcium carbonate as wind-blown dust. Compaction effect in limestone. Calcite undergoes pressure dissolution under the pressure of few hundred meters of overburden, forming solution surface within the rock known as thiolates, according to Butters, 1987. Thiolates are usually high irregular solution surface. They are picked up by concentration of clay, iron oxide, and other insoluble component of rock. They normally form horizontally in response to overburden pressure, but can also form in response to tectonic pressures at high angle to the bedding. At larger scale, horizontal pressure solution surface are within the limestone substation create a parent bedding surface that may vary highly defined by the higher concentration of clay along the surface. Dolomization. Dolomite is a calcium magnesium carbonate mineral that is found in carbonate sedimentary rock of all ages. According to Measure 2003, where the mineral form more than 75% of the rock, it is called dolostone. It is known to occur in small quantities and in coastal setting, where its formation may be related to microbial activity. Burns et al. 2000 and Mazzulo 2000. Most dolomite is believed to form diagenetically, a process known as dolomization. Many dolostone in the stratigraphic record contain fossils which show replacement fabric where material that was clearly originally made up of calcite or argonite has been wholly or partially replaced by dolomite. On the other hand, the dolomization occurs when beds of gypsum are dissolved and reaching groundwaters in calcium sulfate. Sulfate-rich water passing through the dolostone result in the replacement of dolomite by calcite. Diagenesis and carbonate petrography. Distinguishing between cement and matrix and even between grains and cement is not always straightforward in carbonate rock because most of them have very similar mineralogy. Therefore, we can always look at the morphology at the carbonate material to provide insight as to its origin. Grains within limestone that are biogenic in origin usually have distinctive shapes that reflect the structure of the organism. Quartz alloys are easily recognized in intersections. The class of limestone and intraclass have more variable shape and structures, and because they are in fact pieces of rock, they may include areas of cement, which means distinguishing between the cement and intraclass and the latter sediment of the whole rock can be tricky. Neomorphism. Carbonate mud is the main constituent of carbonate mudstone and whackstone and can occur as a matrix in packstone, grainstone, and boundstone. These individual grains are clay-sized and cannot be individually observed with petrographic microscope. Neomorphism of carbonate mud to form microcrystalline spherical site, which this result in an increase in crystal size, thus enables it to be possible to observe the crystalline form under the microscope. Shelly or skeletal material composed of argonite undergoes replacement by calcite to create void later filled by calcite or by direct mineral replacement. The new morphic calcite are larger than the original aragonite crystal, which are often slightly brown due to the presence of material, and it occurs as irregular mosaic occupying the external form of the skeletal material. Carbonate cement. The form of eogenic cement is determined by position of the sediment relative to the groundwater level. In the ferritic zone, in which the pore space are filled with water, the first stage of the formation of a thin fringe of calcite or aragonite growing perpendicular to the grain boundary or into the pore space. These crystals form a thin layer approximately equal thickness over the grains and are hence known as isopacious cement. Above the water level, the sediment in the vadose zone is only periodically separate water, and the cement form only where grains are close together within water held surface tension to form a meniscus. Hence, they are known as meniscus cement. Very fine micritic cements also found at this stage. Recrystallization of eugenitic cement commonly occurs because if their original mineralogy was either aragonite or high magnesium calcite, they undergo changes to low magnesium calcite through time. Dolomite. Most dolomite occurring in sedimentary rocks is diagenetic in origin, occurring as a replacement of calcite. Although the optimal properties of calcite and dolomite are very similar, dolomite commonly occurs as distinctive, round shaped crystal that replace original calcite fabric. Staining the thin section with alizarin grade S 3.12 provides confirmation as the mineral is dolomite, which does not stain pink as opposed to calcite. Post-depositional change to evaporates. According to Warren 1999, evaporite mineral may either be dissolved out of bed in the subsurface or be replaced by other less soluble minerals such as calcite and silica. Dissolution by pore waters passing through the bed leaves vaults and caverns that collapse under the weight of the overburden, forming a dissolution breccia. Breccia formed in this way consists of angular pieces of the strata bedded with or immediately overlying the evaporite, with no sign of transport of the class, which means void between the class may be filled with cement. Initial brewing and heating of the gypsum leads to dehydration and replacement by anhydrite. Conversely, if anhydrite bed are lifted to hydrous near surface environment, a change to gypsum may occur. Replacement of halite, gypsum, and anhydrite by calcite and silica may occur at any stage in diagenesis. The original cubic crystal form of halite may be presented as a pseudomorph, a cast made up of fine-grained sediment. Pseudomorph of selenite, a form of gypsum, may also occur.
Next is diagenesis of volcanic clastic sediment. Volcanic clastic are geologic material that compose of broken fragment class of volcanic rock. All crystal, lithic and vitric particulate material in volcanic clastic deposits are susceptible to diagenetic alteration. Based on Chas and Wright 1987, the volcanic glass will change form when the other medium was absent because it is metastable and devitrified to form very finely crystalline mineral. The volcanic clastic sediment may be completely lost as a result of alteration during diagenesis. Tungsten are kalonite-rich mud rods formed from volcanic, and bentonites are composed of smectite clays that are alteration product of basaltic rocks. The interaction of volcanic clastic material and alkaline waters result in the formation of members of the zeolite group of silicate minerals that may occur as replacement or cement in volcanic clastic succession.
Formation of coal, oil, and gas. The branch of geology that has the greatest economic importance worldwide is the study of fossil fuels, which are coal, oil, and natural gas. The place where the original organic material forms can be understood by studying deposition. Formation of coal, oil, and gas. The branch of geology that has the greatest economic importance worldwide is the study of fossil fuels, which are coal, oil, and natural gas. The place where the original organic material forms can be understood by studying depositional processes. But the formation of coal from plant material and the migration of volatile hydrocarbon as oil and gas require an understanding of the diagenetic history of the sedimentary rock where they are found. For coal formation, coal forms from the dying and accumulation of plant matter before it goes through a physical and chemical transformation. There are four primary stages that lead to coal formation. First, accumulation stage, which plant matter where peat accumulates in freshwater marsh, swamps, and rainforests. Accumulation must exceed the oxidation and biodegradation of the dead matter. Second, burial and preservation stage. Subsidence and freshwater preservation and burial are critical for coal formation. The water is eventually squeezed out. Third, diagenesis stage, which peat is transformed into coal through heat and pressure from geochemical processes that take place underground. And fourth, qualification stage. For oil and gas formation, tiny marine plants and animals died and were buried on the ocean floor. Over time, the marine plants and animals were covered by a layer of silt and sand. Over millions of years, the remains were buried deeper and deeper. The enormous heat and pressure turned the remains into oil and natural gas. Today, we drill down through a layer of sand, silt, and rock to reach the rock formation that contain oil and natural gas deposits. Naturally occurring oil and gas are principally made up of hydrocarbon compounds of carbon and hydrogen. The eugenesis eliminates oxygen from hydrogen, the solid part of the organic matter that is insoluble in organic solvent. There are three main types of hydrogen are recognized. Type 1 is derived from planktonic algae and amorphous organic material and is the most important in terms of generating oil. Type 2 consists of mixed marine and continental organic material, algae, spores, particles, which form gas and rapeseed oil. And type 3 originates from the terrestrial woody matter and is a source of gas only. Formation of oil. First, the organic matter must include the remains of planktonic algae that will form type 9 hydrogen. Second, the organic material must be buried in other like ketogenesis can generate liquid hydrocarbon within the correct temperature window. The third factor is time because the hydrogen source rock has to lie within the oil window for million years to generate significant quantities of hydrogen. Gas consisting of short chain hydrocarbon, principally methane, is formed from type 3 hydrogen and at high maturation temperature. The methane generated from coal may become stored in fractures in the coal, same as coal bed methane, which is a hazard underground coal mining but can also be exploited. Oil and gas reservoirs, hydrocarbon traps. Oil and gas become trapped in the subsurface where there is a barrier formed by impermeable rocks such as well-cemented mud rock, and evaporite beds. Reservoir rock. Almost all oil and gas accumulation occur underground within the pore space of beds of sedimentary rocks. The reservoir's quality of a rock is reduced by two main factors. First, the presence of mud reduces both porosity and permeability because clay minerals fill the space between grains and block the fluids between them. Cementation reduces porosity and permeability, crystallizing minerals in the pore space, sometimes to the extent of reducing the porosity to zero. Economic oil and gas accumulation. Exploration for economic reserve of hydrocarbon requires knowledge of the depositional history of an area to determine whether suitable source rock are likely to have formed and if there are any suitable reservoir and capitalities in the overlying succession. This analysis of the sedimentology is an essential part of oil and gas exploration. Knowledge of post-depositional event is also important to provide an assessment of the thermal and burial history that confers the generation of hydrocarbons.